splitting in the omega 1 direction, which is rather annoying because it gives rise to line broadening. For example, this is a omega 1, omega 2 decoupled carbon-proton correlation map. But you see some splittings in the proton frequency direction, and that is because proton-proton splittings are not killed. The proton-proton couplings are still alive during this experiment during T1 period. And therefore, it would be highly desirable that we can remove these couplings. There is a scheme which is called a bilinear rotation scheme with an acronym of BIRD. And I do not know whether we will have time to go through how BIRD works. I have an appendix, an analysis of how BIRD works, but if you get time, we'll go through it. If you don't get time, you'll read it yourself. But basically what it is, that we apply a sequence of pulses in the middle of the T1 period with the two tau periods introduced. And what it does is basically it removes all other interactions and keeps only the proton chemical shift as a effective Hamiltonian during T1. Okay, so the proton-proton chemical shift is gone. The proton-carbon chemical shift is gone. Proton-carbon J coupling is gone, and this is how it basically works. Okay, and rest we have this tau 1 period for bringing the antiphase into in phase, and we have a tau 2 period for bringing antiphase into in phase, and this sequence then finally gives us the desired spectrum, which has both which is omega 1 decoupled, omega 2 decoupled, and proton-proton couplings also removed. And you can see this gives very sharp lines, and then if you take a larger molecule, you can really assign quite a lot of the spectrum with the help of this technique. Oh no. Is the page number incorrect? Oh, my numbering is wrong. I see. I'm so sorry. I must have flipped my mind while numbering them. I don't know why it went back to 4. But they're rough to lecture number 6. So you have the right folder though. Please correct them in that. They say 4, I don't know. Okay. See, I have not numbered my transferences because I want to use them in different ways in times. But some of the later lectures I have numbered my transferences. So. All right. Mm-hmm. Okay, we go back to page number 8. Now, this point of time, several people had started thinking about whether it's necessary to collect a two-dimensional data set or not. And several developments took place because of converting this two-dimensional business into one-dimensional experiments. And it might be appropriate to talk about at this point of time how to convert that. I mean, it's easy to do one-dimensional experiment, but how to convert this two-dimensional algorithm into one-dimensional. And it's always the question that whether these experiments were thought of first and extended to two-dimensional, or if these experiments of one-dimensional were actually a conversion of two-dimensional experiment into one-dimensional. One can argue about that. All right. Well, it's rather easy in this case that if you just, for example, make a fixed period of T1 period and not make it an incremented period. Just take one experiment in which the T1 period is fixed to some number tau and do the experiment. Then what you get is what is a well-known experiment called, it was named as INAPT, although it's a very good experiment, but the acronym is Insensitive Nuclei Enhanced by Polarization Transfer. And it's by Morris and Freeman in 1979. But this is well after development of 2D. So I would call it an extension of 2D, okay? Although it's a 1D experiment, and one could think about it even without doing 2D. But basically what it is doing is exactly the same. We have a, for example, in this case, suppose if we don't look at the 180-degree pulse, then we have simply the polarization transfer experiment from proton to carbon. Okay, and really the 180-degree pulse is just making the transfer insensitive to the chemical shift. Okay, and so we just put the two pulses. If we had put only one pulse, it will also kill the J coupling, so we will not have any transfer. So we need to put both of them. All right, you can do without that, but then your transfer will have some dependence on chemical shift, and so this is the basic reason for doing that. And what we are essentially doing is we're creating this antiphase state, which is then converted into a Y magnetization, which can be detected. It's a polarization transfer experiment, exactly in the same way that we have described the 2D experiment, but we don't have to collect a two-dimensional data set in this case. A 1D data set will do, and we get decoupled carbon spectrum, which then can be looked at, and depending on the value of tau, we have CH, CH2 or CH3 intensities, which are quite rapid functions of this. It's very sensitive experiment to the value of J versus tau. This particular experiment is very sensitive to value of J and tau, and you can get into a lot of trouble. And therefore, an experiment called refocus INAPT was designed, in which some of the sensitivity was there are two ways of looking at it. One is the sensitivity to J, other is that you want to decouple during T2 dimension. And so you have to throw in the delay and the pi pulses along with it, and this gives you what he calls a refocused INAPT. And in the refocused INAPT, now we know that we are in the carbon domain, so we will have sine cos and sine cos square dependence, and in the proton domain we will have just sine J tau dependence. Okay, this is what I said before, and this is exactly the same thing. The dependence on tau prime is again plotted here, which is exactly this one I plotted before, and so we can then decide whether we want all of them, or we want select some of them, or we want to do editing. And this experiment is then used quite often. In fact, it is some kind of a replacement of off-resonance decoupling experiment, and it's a much better experiment to do than off-resonance decoupling. I think off-resonance decoupling is not done anymore. Everybody does this INAPT or refocused INAPT type of experiments, or there are many other modifications of these experiments that have come up in recent years. For example, even if you were looking at, say, for example, a methyl group, you would want that the methyl group should come out with undistorted intensities, but it's sensitive to these. And if you have one methyl group having one J, another one having another J, then you don't get it with the same intensities. This sensitivity is removed or taken away somewhat in an experiment called distortionless polarization transfer experiment, a DEPT experiment, a very powerful one. And what it attempts to do is to take away the tau dependence and put it into a dependence on the angle of this pulse theta. Okay, so remove the tau dependence and puts in the angle of the pulse theta. And it uses double quantum coherence, so we should digest it without having learned about double quantum coherence. And it removes one period and combines the refocusing of I with defocusing of S. That means there is a this period and this period are overlapped. Okay. Furthermore, the chemical shifts of the I spin and S spin are focused by these 180-degree pulses. And so basically the aim of the 180-degree pulse is to just refocus the chemical shift of the proton and carbon before the transfer and after the transfer respectively. And for the looking at how this depth works, we will then therefore ignore the 180-degree pulses completely. Just we'll assume that there is no chemical shifts playing any role. And therefore we have at this point of time before the 90-degree pulse on the I spin magnetization in the state Iz. And application of 90-degree pulse brings it in the Y direction, 90-degree X pulse. And then we have this evolution by one delta, which is half J. And this half J evolution brings this state of Iy into IXSZ state. We already know that if we put delta equal to 1 upon 2J, it will do that. We have removed the 180-degree pulse from here, which will remove the chemical shift dependence on that. But that doesn't matter. Okay. And then we have this state here at this point of time and apply a S 90-degree pulse, and we get twice IXSY. Okay. Now twice IXSY is a what we call a heteronuclear double quantum coherence and zero quantum coherence between I spin and S spin. And its evolution, how it evolves underway in this CH2 and CH3 coupling, we will actually look at it when we do the product operator algebra. Okay, but the result I'm giving you here. The result is interesting. For example, this double quantum coherence does not evolve for two-spin system. Okay, it has perhaps it's easy to see in this it is actually independent of the coupling value, the frequency of that. Okay, this does not evolve under single coupling, but this one does evolve, and only it evolves in such a way that as if there is a third spin, which is just remains Iz. So but it becomes Ix, Iz, Sx, and this one also evolves. So this is what happens. I mean, how exactly in detail it happens, we will look when we go to product operator algebra. This is the result. And if we do not have delta exactly matched to 1 upon 2j, we will get other terms which do not contribute to signal. And this is the secret of this experiment. That is, we create terms which are, when their delta is not matched to j, we create terms which are not observable. Okay. On the earlier experiment, when the delta is not matched to j, we get terms which are observable. And here we get terms which are not observable. And that is actually the secret of this experiment. And this state of what we have is some kind of a let me put it this way. All these are double quantum coherences. Okay. All these are double quantum coherences. This one is a pure double quantum and zero quantum coherences. Coherences of order 2. This is also a coherence of order 2, but antiphase with respect to the third spin. This is also a coherence of order 2, antiphase, doubly antiphase with respect to two spins. And what this theta pulse does, that it converts part of this double quantum coherence into observable magnetization. And you see, this is how it will do it. Okay. For example, the IXIY on application of theta pulse on the I spin along the y-axis will give us a Ix Sy, because it's a will Ix Sy cos theta plus Iz Sy sin theta. Because what it is trying to do is to convert x into a z component. When you rotate about y, x is getting converted into z with an angle in between, a theta angle. And so we have a cos theta Ix, a sin theta Iz. Okay. And so this again is a double quantum coherence, not observable. This is a single quantum coherence, which is observable. This is a single quantum carbon coherence. And this is observable. And it has sin theta dependence. For a CH2 group, it has sin theta cos theta dependence, and this is a sin theta cos square theta dependence. And this then reminds us exactly of this picture here. Back to this picture. And so what we have done is, we have converted the delta J dependence into a theta dependence. Okay, and so the multiplet we get is then undistorted. Of course, you can then say, what is the 2D version of the depth experiment? I mean, we first had a 2D experiment, then we went to 1D experiment. We come back to the 2D. And what is the 2D version of the depth experiment? Very straightforward, that you just convert the fixed period, the delta period, into a T1 period. Okay? And that's what we have done here. We have converted we have converted, we have added a T1 period. We have added a T1 period to the one-dimensional depth experiment. We have just pulled this proton pulse out and added a T1 period. Okay. And we want to do decoupling in omega 1 direction. Therefore, we apply a pi pulse in the middle of the T1 period on the carbon 13. So we pulled this from the depth 1D version to depth 2D version. We just pulled this proton pulse out from here to here, added a T1 period with a pi pulse in the middle on the carbon to decouple it. And so this is the 2D version of depth. You can interchange this T1 period with the delta period and put the delta period before. We did this in Super Cozy also. And so this is interchangeable. Except that if you look at it, that the B scheme has one pulse less, but it still works. Okay. Now, at this point of time, we will get, suppose we had put our theta or delta somewhere at this point. Okay, delta in case of inapt experiment and theta in case of depth experiment at this value. Then we will get CH group, CH2 group, and CH3 group, all of them. Or if we had put it here also, we will get them, all of them. And sometimes it may be interesting to separate them out, which are CH and CH2 group. Of course, with this, we'll get positive negative intensity. Another way of separating them out is to change the angle of this pulse. Okay. And okay, this one way is to change the angle of the pulse. What I have said in this transparency that I put the angle here, then I will get the CH and the CH3 in the positive direction and CH2 in the negative direction. Other possibility is to increment the angle of this pulse along with T1 period. This is called an accordion experiment, and basically what you say is, for one value of T1 you have one value of beta, next value of T1 you have another value of beta. The formula for that is given here. If you do this, the beta dependence is getting Fourier transformed, and it shifts the CH, CH2 and the CH3 groups in the omega 1 frequency domain. And the result is this. Okay. So you get CH3 groups at one frequency, CH2 groups at another frequency. Of course, you must choose the angles far enough Well, that's already because of the formula, it already takes care of that. And then you will get them separated out. Of course, in the CH3 case, and CH and CH3 will be, you will get both of them because they have both. This CH group has a frequency half J, CH3 also has a half J. So when you try to get CH, you also get CH3. This gives you CH3 only for the outer lines, and these give you CH3 for the inner lines. Okay, and so you get them, all of them. All right, so for these experiments that we have talked about, the correlation experiment, the inept depth, and depth with various angles, etc., we have focused our attention on the direct carbon-proton one-bond coupling. And we have talked about this interval J, interval delta, which is tuned to 1/2J. And when we talk of J, we mean the direct coupling. But nobody stops you from making this delta equal to 1/2J, where J is long-range coupling. If you do that, then it will bring those antiphase components in phase. Okay, so in fact, all these experiments that you can think about as they belong to the direct coupling, direct carbon-proton one-bond coupling, or to a long-range coupling. And the correlation across more than one bond is more interesting. You know, identification of carbon-proton one-bond is quite useful because this helps you in assigning the spectrum. But if you have a correlation across more than one bond, it will help you even more because perhaps you could even do what called a relationship where which carbon and which are near to each other. Okay, and so the correlation across one bond is more interesting. There are two ideas about that. One is that you do a correlation as JCH correlation. That means you have the direct coupling, the carbon coupling to the proton is what you try to correlate on long range. Or you do a relay experiment. That means you transfer magnetization from one proton to another proton, which is directly bound to a carbon. Okay, and this is the idea of the relay experiment, and this is the idea of the long range correlation. And both will give you correlation across more than one bond. In principle, of course, as I said, you could tune delta to large, to smaller coupling, in which case delta will become large.